Pleased to come to the end of our tutorial session, which has been very enjoyable, with Oscar, who's going to finish off the tale of entropy and majorization.
Thank you. There's actually going to be a little tale as part of the presentation. So in the first talk, I went through entropy. Right? So entropy is one way of quantifying the idea of randomness. But now we're going to talk about another related but a distinct way of quantifying randomness. And at first, at least for me, when I encountered this, I felt, oh, this is quite artificial or technical. But now I'm quite convinced, and I hope to try to convince you that it's a very natural way of quantifying randomness. So it's called majorization. Before giving you the overview, let's just say briefly what it is. One way of saying what it is, which is a more technical way. Okay, so consider a probability distribution over some sample space. So just P1, P2, P3, and so on. And now you zap this with some randomizing map. So you move the underlying events around somehow. This should make the probability distribution more random, still, in some sense. I'm going to be much more precise about that later, because that's a dangerous statement. So very often this relationship is actually what's called P majorizes P prime. So the initial probability distribution majorizes the one after the map. And you can write this in this way, which is going to look a bit arbitrary to you maybe. So this arrow means that you order the distribution in descending order. Then you sum over the entries up to entry k. And to have majorization, you demand that this guy is bigger for all k than this guy. And I will discuss why that is and so on, and how to visualize it. I also briefly now mentioned already that the quantum case is the same, that you say that as density matrix rho majorizes rho prime if the eigenvalue spectra obey the same relations.
So you refer to finite space here?
Finite spaces, yes. So the overview is it's going to be classical majorization to start with. Actually, there's an extra entry here which will come next, which has to do with wealth inequality. Then there's doubly stochastic matrices and majorization. And then a really nice way of visualizing majorization geometrically. What's the relation between majorization and entropy? What does this have to do with thermodynamics? I'm not going to talk too much about that, just a little bit. Then we go into the quantum case, briefly saying what the corresponding geometrical visualization is. And then some slides on entanglement theory, because there is a very important result involving majorization and entanglement. And then I'll discuss a bit about quantum thermodynamics. Finally, very little on majorization in GPTs. And as I mentioned in the first talk, I see this as sort of preparing you for two talks that are coming later in this workshop. And both of the authors are here. I'll cite their papers later. But first, okay, so a story about wealth inequality. So I found it a bit hard to get my head around the graph I'm about to show you, and I found it helpful to think in this way. So this is an extremely contrived story, okay? But it's just to remember how the graph goes. So if you take, let's say, okay, there were two kings, okay? And they wanted to compare who had the most inequality in their land. Okay, I'm not sure if I should assert whether they who would win, the one with the most inequality or the one with the least. Okay, you can choose what you think would be more likely. So how could they compare that? Well, they came up with this clever scheme that they would get the people to be arranged. This is a little bit contrived, possibly. That people would be somehow they would manage to arrange them according to wealth. Okay, and so starting with the poorest, and moving up to the richest. So this axis is now people. Okay, the number of people. And each one would somehow show how much gold they had. Maybe you can visualize that they actually brought it to a square. I don't think they would, but let's say that there was a square and they had to bring it there and put it in a pile, okay? And then here you have the wealth that has been counted, amassed, so the pile of gold, okay? So the sum of everything that's been collected. And then it's going to rise, okay? Somehow it's going to rise and it's going to go up to some max value.
Shouldn't the gradient be getting steeper?
Is that the total?
So there can be said that now this is very important. Yes. Sorry, I'll get to that. But there was a
I was just asking, is this the total wealth up to a certain point?
total.
Up to
So it's the pile. So they're making this pile of gold.
Yeah.
So this is like the size of the pile. Okay. So now, if you have a very equal society, so let's say that everyone has the same amount of money, then it is a straight line. So I think it's a uniform distribution of wealth, and then you just sum it together, you get a straight line. But of course, in practice, it's going to be sort of quite slow in the beginning, right? And then at the end, the rich guys come and boom. Okay. So these curves are called Lorentz curves. So, for example, if you Google these things, you will find lots of economics articles. So this one is from the World Bank, and I guess they've chosen these as because they're actually almost different extremes of these indices. If you look up different countries, I'll describe what this means in a moment. So there's two countries, Hungary and Brazil, and each one has a different Lorentz curve.
Is that a physicist?
I don't know.
Other
You know, I don't actually know the answer to that.
No.
Does anyone know? Could it be the Lorentz transformation? Same.
He has a G in his name.
Oh yeah.
The
That's
chaos, the
Oh.
tractor Lorentz,
Yes, that's right.
different, spelled the same way.
Uh-huh.
No, but he would be later. Forget.
Yeah, I don't know.
Sorry.
Okay, so there's two countries on this graph. There's Brazil and there's Hungary. And each one has a pile of money that sort of gets summed up, which I just write like Brazil of K. So you sum up these things. I guess they create histograms of people, and then each histogram is labeled by K. And then they sum them up, okay? And then you get this line, which is the line of absolute equality. And now these guys come in under that line, as someone just predicted. They will get steeper as you get to the rich people. So Brazil is one of the most unequal countries, according to when you look at these graphs, and Hungary is one of the most equal. And this is Gini index, which they define as the percentage of this yellow area under this equality curve, which happens to be above the Lorentz curve. Okay? So they put a number to it like that. So Brazil has a much higher Gini. It's more than half of the area is above the curve. Brazil. Is this okay? So, I don't need to do that. So now you do the same kind of thing, but for probabilities. And annoyingly, we're going to flip the order, so we're going to start with the highest probabilities. Yes. So maybe I should even delete this before you get confused. So we can make these Lorentz curves for probability distributions. And we can use these to define majorization. So we're going to order the distribution in a descending order. And you draw your probability distribution like a step function. And the corresponding Lorentz curve, maybe I can draw it under it like this. Call it L. It's going to look like that. And because these are probabilities, they work their way up to 1. So this is the Lorentz curve. So do you see what I mean? This is a sum. I'm just taking the sum of these guys. So like the integral of this thing. So this is the same example. Same kind of example. Lorentz curve on this axis and this kind of event index going this way. And it flattens out. When it hits 1, it doesn't go further because I'm assuming it's normalized. So what does majorization look like in terms of these curves? So we can equivalently state it as the Lorentz curve must upper bound the other one at all points. So for a distribution to majorize the other one, the Lorentz curve of that distribution must upper bound the Lorentz curve of the other one at all points. So in this case, again, here's the Lorentz curve. This is this event index. The black distribution, this is the Lorentz curve of the black distribution. It majorizes the red one. So upper bounds it at all points. In this case, and this happens for if you write down the random distribution, it may well be the case. They cross, okay? So what do you do then? You say, well, actually, by the definition of majorization, it's not well defined. You can't say that one majorizes the other. In the case of the wealth inequality, it would mean that if you have, I assume it happens there too, that the two curves would cross, so somehow maybe one country is more equal in the lower end of the wealth spectrum and the other one is more equal in the higher end of the wealth spectrum. So majorization is not always defined. So one key reason why you should think it's natural is this thing that is related to a type of randomizing map called a doubly stochastic matrix. So what are these? Okay, so we discussed stochastic matrices in the first time, but I'll go through it again. So let's say we have some two possible sides where you can be 1 and 2, simplest case. If you have a sort of random walk that you can hop between these things, then the simplest scenario would be that you have these 4 possible hops now. Each one has some probability of happening, right? And the probability distribution of being on site 1 and site 2 evolves according to a matrix. But this is actually now by assumption, you're assuming that it's this type of random process.
Get your errors next.
Have I got the errors the wrong way around? The 1 and 2 and 2 and 1.
Yeah.
Okay, sorry. Okay, so yeah, 1 should go to 2. So then we have this matrix has these entries that are transition probabilities. So for example, P1 prime is equal to the probability of staying in 1 times probability of 1 plus the probability of hopping from 2 to 1 times the probability of 2. Right? Okay, so now these matrices are stochastic if the entries in here are probabilities, so real numbers between 0 and 1, and the columns sum to 1. They are doubly stochastic if they are stochastic, and moreover the rows sum to 1. And if you demand that a stochastic matrix leaves the uniform distribution invariant, that forces it to be doubly stochastic. So that's, you can see that as a key difference between general stochastic matrices and doubly stochastic matrices. Maybe you can imagine that if you put in 1 over d here, and you demand that to be invariant, that it forces the rows to sum to 1. So this is this theorem that if you have a matrix, it's doubly stochastic if and only if there is a majorization relation. Sorry, maybe this notation, did I define it? So this means majorizes, okay? I may have flipped the order there actually. So I've tried to use the convention throughout that this should be the other way around. That this guy is, okay, this should be the other way around, okay? And that means this one is more ordered than that one. That's the convention I'm trying to use in this talk. So, for the proof, I direct you to this Bible of majorization. So I'm going to try and stick with the more sort of visual proofs rather than the ones that have, lines of sums. Okay. This is it's called Inequalities Theory of Majorization and its Applications. It's this thing. Okay. So, but let me give you some examples. Okay. So one is if you do now coarse graining. So we talked about that the other day, right? This is something that's not going to give you a more random distribution in general. It just gives me this. And as you might expect, M is not doubly stochastic. The M that does that. You see the sums, the rows don't sum to 1. A slightly more interesting map maybe is the one that maps anything to the uniform distribution U. So that just means 1 over 2, 1 over 2. You can write it like this in bracket notation, so it's a vector, the bra of 1, 1, and the ket of 1 over d, 1 over d. And if you write that out, it looks like this, as it should. And that would give you the uniform distribution. And that is doubly stochastic. Then, these guys, if you just think of this now as some abstract set, these matrices, it's a convex set. So probabilistic mixtures of these matrices are also doubly stochastic. So you can form this set by taking the convex hull, so all probabilistic combinations, of the permutation matrices. So the permutation matrices are the ones that look like, so for a single qubit it would just be this one, not qubit, sorry, single classical bit. So they permute the entries in the probability vector. So for example, this one that we just saw is a probabilistic combination of these two. So that actually, one reason why that's really neat is that it allows us now to visualize majorization geometrically. So because doubly stochastic matrices, like just stated, are equivalent to probabilistic combinations of permutation matrices, we can visualize what they do. We can create an orbit of states that can be accessed from the initial state by permutations. And the resulting state then, when you take a probabilistic combination of permutations, must be inside the orbit, so inside the convex hull of the orbit. Let's do a very simple example. So if we have P of 0, P of 1 is 0.8, 0.2, okay? then with these two permutation matrices applied, I can either do the identity or I can do the flip. Okay, 0.2, 0.8. What does that look like? So on this axis is P of 0, on this axis is P of 1. So that state goes here, somewhere, and that state goes there. So if you start in this state, and you want a state that's majorized by that one, it has to be inside this area. I think this is really neat. Like if you just think about it, if someone now tried to ask you to, from scratch, define what makes a probability distribution more random than another, right? Then you would probably say, oh, if I have 0.8, 0.2, and 0.2, 0.8, these guys are as random if you believe that permutation doesn't change it. But if you take a probabilistic combination of these guys, if, okay, that's probably more random, I'm happy with that. So we can do this in 3D. I was very happy when I realized this, that you can visualize in 3D. I mean, this will have been known by various people, but you can visualize in 3D why some distributions don't majorize each other. Okay, so let's think about these two cases. So this guy has an orbit. So that just means a set of permutations of it, which includes itself. And that is the blue. Those are the vertices of this blue triangle here. The blue triangle itself is the convex hull, so the probabilistic combination of all the states, all the probabilistic combinations of these three states are inside here. So then you see that, okay, this state, 2/3, 1/6, 1/6, actually which one of them is that state and the other one is the permutations of it. Okay, so anything on this, let's just say this is one of the states on the orbit. This guy is outside of this triangle, right? So that means this guy is not majorized by this state. Similarly, this guy is not majorized by this guy, by the red ones, because it's not inside this set. So this wouldn't happen in 2D, but it can happen in 3D. So, okay, then what's the relation with entropy? It's very simple. That if P majorizes Q, then the alpha entropy, if you remember these Renyi entropies, so that was this. The alpha entropies are bounded each other in this way. So that's kind of what you would expect intuitively. But it's not the other way around. So if you take two distributions that do not have a majorization relation, so for example, if you just write down these guys, well, if you choose them such that they don't majorize each other, I don't know if you can see already now that they don't, so unless I've messed up. So this one looks like easy way of checking, and I guess that's the key reason why we write down that majorization condition in terms of the Lorentz curves, is just to draw the Lorentz curves, and then we see if they cross. So the first one goes up to 8/12, and then it flattens out. And the second one goes up to 6. And then it goes up to 11, so it's here. And then it goes to there, okay? So those two, they cross, okay? So there's no majorization relation. But I can guarantee you that if you evaluate the S alpha for these, they won't be the same. They won't, they're not going to be the same number. So you can't therefore say that, oh, because one entropy is greater than the other, there is majorization. Okay, so here is, when we were working on, and Horodecki and Oppenheim, and so this is Daria Egloff and me and Renate Renner and Vlatko Vedral, when we were working on thermodynamics, a measure of a way of putting a number to how much something majorizes something else came up. So the definition is that you have a Lorentz curve, define this measure, which we're just calling the relative mixedness. Define it as the maximum m such that the Lorentz curve of this guy upper bounds the other one at all points. So this is like a stretching factor. So m is the maximal amount by which one can stretch one of these guys such that it upper bounds the other one at all points. So here's an example. We have this axis x, and here's the Lorentz curve here. So we have, this would be the black Lorentz curve. It majorizes the red one, which I chose to be a uniform distribution on some events for simplicity. And it majorizes it in such a way that I can stretch it, right? So I can stretch this guy along, which is what changing this x means for one of them. I can stretch it along to this dotted line, and I can stretch it from 2 to 3. So the m is actually 3/2. It's a little bit annoying that it's an optimization, but for example, it's nice that it's only going. Actually, normally we take the log of it even for thermodynamics, and then it's only non-negative if there is majorization, unlike, say, the Gini coefficient. And now I should mention that Paul Bush and others, Mead, they have done something called a paper on the measure cone, and there's a notion of quantifying majorization, which I'm hoping to learn from him, because I don't actually know how it goes yet. But there are some papers. These are probably from 70s or 80s. Is that correct? Yep. And so there probably are existing alternatives for quantifying majorization. So in the quantum case then, so as mentioned, we say that rho majorizes sigma when the eigenvalue spectra majorize each other. And it was shown here that this is actually equivalent to demanding that sigma is a convex combination of hitting rho with unitaries. And I think that these talks that come later in the workshop will center a lot on the relation between these two claims, if you don't assume quantum theory. So this is actually very similar to the classical case, where we said rho p majorizes p prime if we can get p prime by a convex combination of hitting it with permutation matrices. So we can visualize it in the same way, although it would be nice to go to the qubit, but I don't know how to draw that. It's too high dimensional, so let's do qubit. This is a block sphere. So again, we start in some state, and we can take the orbit of states that are accessible via reversible transformations. And you know, if you look at the block sphere, so the block sphere is right that you take just because I know that not everyone is from quantum stuff. So you have these Pauli matrices. I probably shouldn't write them out. You have the Pauli matrices, and then the expectation value of one of these guys. It can be derived from the state, which is this density matrix, matrix with complex numbers, combined with this, these matrices. So then you get a real number that represents the expectation value, and it's between 1 and -1.
I think that X is supposed to be a G.
It's supposed to be what, sorry? Oh, G, thank you. So this is the block vector is a vector of these expectation values, and it's actually enough to define the state fully, even though you can do other measurements. So therefore we like to represent the state of these small systems qubits with this vector. It's a real vector. Okay, so there is an orbit here, which is, so a unitary in this representation is an orthogonal matrix that rotates you. So this purple, whatever color it is, thing is the set of states that can be accessed by rotation from this original state. Okay? And if you take convex combinations, so imagine having these vectors and you put P in front and you take convex combinations, then you end up inside this sphere. So for example, if you take this guy combined with this guy, then you end up somewhere in between. So if you want the states that are majorized by this guy, that this guy majorizes, they're going to be inside this thing.
So for any two density matrices for a qubit, rho and sigma, either rho majorizes sigma or sigma majorizes rho.
Yes, I think that's true.
But in general, that's not.
No. So this is like, yeah, in general. So there's like with the classical bit case, that thing would be true, I think, for classical bit, but not for trit. So one of the reasons why these things are known by some people in the quantum information community is this stuff, which is that it has to do with entanglement transformations. So Nielsen in particular showed that this is for the kind of scenario where you have a state which is actually kind of shared out between two parties, Alice and Bob. And then they are allowed to do stuff on their own. And then this is subtle. They can send classical messages to each other. So meaning that B can choose to do transformations conditional on Alice's outcomes. So they can do. So now there can be a sort of cross influence here, in the sense that the next transformation, this could be TB1 for the T1, say. And then Bob does, actually let's write it like a quantum map somehow so that this is better notation. EBT2, which could depend on Alice's outcome. So they're allowed to do this, these sort of things that they do operations on their own sites, and then they can do operations on their own sites conditional on what happened on the other side. And this is called local operations and classical it's abbreviated LOCC. So he says, okay, suppose they possess a pure state, a joint state, and they can use local operations on their respective systems and classical communication. And their aim is to transform this guy into another state, phi. So at the end, they want to have this state phi A, AB shared between them here. And what Nielsen proved is that it's necessary and sufficient for this to be possible to have the density matrix spectra of the marginal states, so the states individually on Alice or Bob, they actually have the same spectra, that they have a majorization relation. And it goes in the majorization relation necessary and sufficient for this transformation, kind of goes the wrong way from what you might somehow instinctively expect. So I will try to explain what's going on now. And there's also related work by many others, including Vidal and Jonathan and Plenier. So you want to convert phi to, actually I guess these are both phi's. You want to convert this state to this state, and you're not allowed to use entangling operations, but rather you're allowed to do Alice measures, and then they both do a local map depending on the outcome. That's slightly more restrictive than what I just said, but actually it's been proven by Lowe and Popescu that it is the most, that you can do anything this way for pure bipartite states. So let's just say that you do that. Alice measures, and then they both do a local map that depends on the outcome of Alice's measurement. So the new state will have this form. This is the thing that updates Alice's state. That's her original state. And that's the map which actually I'm writing now as acting on Bob. So I'm going to, anything Alice does, I'll absorb on here. So it's a map afterwards that depends on M. So it depends on what Alice gets. So a simple example is that if this is your state, Alice could measure in the 0-1 basis, and then it collapses to this versus this. And then if, depending on the outcome, they do corrective unitaries. So in this branch, you have to do X flip on both the bits. And now this very simple example, which is definitely not the most general example. I have one more general example on the next slide. But you can already see here that if you look at the reduced state, and now this is the tricky part, is that you have to go backwards in time to see where the majorization relation comes from. Look at the reduced state of A here. You see it's more pure than the reduced state of A here. And if you wanted to go backwards, you would undo the unitary that you did, and that would have to be probabilistic if you want to recreate the same initial reduced state. So actually the initial reduced state is a probabilistic combination of applying unitaries to the final state. So the reduced initial state is the other way around. So this is more random. What did I call the other one? Phi? So slightly fancier example of that is that now you have to think, like, how can I convert this sort of thing to that? Well, you can do it by using an ancilla locally on Alice's part, followed by and then a measurement on the ancilla, followed by conditional local unitaries. So here's the state you're interested in. Now you add this ancilla, and just because it works, you put it into this state. Now, if you think about it, you will see that there is a gate that acts, a unitary matrix, that acts on these two things. This one is Alice, and this is Alice's ancilla, okay, this whole thing. So you can do a unitary that acts only on Alice's part, that takes this state into this state. And you probably have to do the calculation to believe that, but just believe it, and then you see that if the ancilla is in 0, you collapse to this, and if the ancilla is in 1, you collapse to that. So let's call that long thing the square bracket. The square brackets get split into this, depending on, and this now when Alice does her measurement. So there's a branching again. And then you have to do a corrective unitary in one of the cases. So here you have to do an X flip on Bob's side, and then you get this. And also here, if you go through, you can convince yourselves, if you go through the calculation, that actually you can recover the initial reduced state by undoing unitaries like this on the final one. So that is a majorization relation. Okay, so that's not a proof of Nielsen's theorem. It's just to give you a picture of how to remember which way the majorization result goes. So Nielsen's theorem says that LOCC conversion of pure bipartite states is possible if and only if the reduced state of the initial state is majorized by that of the final. So that's this equation. So then there's this whole field called entanglement theory, which is about how to quantify entanglement, and obviously it's very influenced by this result. So in particular, if we look at any 2-qubit state, this guy can be converted to any of them, because this has uniformly random reduced states. So if you look at this guy, the local state analysis side is half-half. It's the maximally mixed state. Because this can be converted to any, sort of the most valuable one, it's taken as a kind of currency of entanglement. But now you may wonder, okay, I've been taught that you should use S of rho A, the entropy of the reduced state, to quantify entanglement. How do these things fit together? And now, if you remember this IID thing from the first lecture, that if you have IID meant that your total state, and let's write it as a quantum state this time, is equal to some so this just means sigma. So that's the tensor product, is the way that we combine systems when they're independent. So this is IID. Independently means it's this thing, and identically means it's the same state everywhere. So independently, identically distributed. And if you remember, as n goes to infinity, the number of so the probability of a typical string, or close to approximately a typical string, goes to 1, and the number of typical strings which I call n-tip, is 2 to the n-h, or s, whatever, let's call it s now. So effectively we have a uniform distribution on this many states if you have a large n state like this. So that's just what I'm saying here, is that you effectively have a uniform distribution of this dimension on Alice's part. So you could say that means now effectively you actually have n S of row A EPR pairs. So in that sense you could say, oh, it makes sense to use S of row A as a figure of merit. But you should also remember that if you just have one copy of the state, then even if the entanglement entropies are in the right direction, you cannot infer that LOCC conversion is possible, because majorization is not guaranteed. So you can easily make up some examples where this is the case. So it's just instructive to do that. So if you want examples of distributions that don't majorize each other, you remember you have to go to at least 3 entries, and you have to make the Lorentz curves cross. So if we have, it's usually a good idea to have something that starts steeply and then goes flat. And then you have something else that sort of starts a little bit less steeply and then goes up, and then like that, okay? Actually, I must have had an example like that before in the previous one. Maybe I can just use those numbers. This one, okay? So if you have these two states that you now take and now hopefully those of you who are familiar with taking reduced states will see that that gives these things as the reduced state. Then the phi would be the corresponding one. These guys will not be LSCC convertible, but you will have one of the entropies will be bigger than the other. But then, oh, sorry, wasn't expecting that slide. Good. Okay, but then there's like for any Nogo theorem, there's a clever trick. So in this case, this is an example due to Jonathan and Plenio. So if you look at this guy, it does not majorize that one. But if you now add this extra system, and it's going to act like a kind of catalyst because it's unchanged, it does. You can check it. You can go through the numbers and check it does. So when such a catalyst exists that gives majorization, then you say that there is trumping. This is as opposed to standard. So you're unhappy with that definition?
Strange word, but
Yeah. Okay.
as in Trump when we play cards.
I guess that's where it's from. So you say this trumping as opposed to standard majorization. So this example, then together with Nielsen's theorem, demonstrates that there's actually there are cases where adding a catalyst makes LSCC conversion possible that would otherwise not have been possible. Okay, so now just a very brief comment about this more general scenario. And there are 2 talks on this at the workshop, and I'll show you the titles in a moment. But just to get you thinking about it. So the question now is, what if your states are not necessarily quantum? And we're in this framework that we can nevertheless represent them as real vectors. So as if you can represent, there is a framework where you can actually represent quantum theory as real vectors as well. I should have said that. But there's many theories in that framework that are not quantum theory. So remember, theory means what set of state vectors do you allow, what set of effect vectors do you allow, what set of transformation matrices do you allow. But can you define majorization there? Because we don't have necessarily the notion of an eigenvalue spectrum if we just have a data table with a real vector. Okay, so the one that sort of jumps out to me as the natural one from these quantum and classical cases, and apparently this is pursued in a paper by Massanes and Müller, is that you can say that sigma majorizes rho. This is now for the vectors. These are real vectors representing your states. So in the quantum case, it would be the Bloch vector, for example, or generalization of the Bloch vector. That you say that's true if you can form the new one, if you can form rho by randomly applying reversible transformations on sigma. So Ti are the reversible transformations. So in the quantum case, they would be unitaries. In the classical case, they would be permutation matrices. So just a simple example of that. So let's see. Now, if you have this, a square as your state space, then you can rotate it at certain angles and recover the same square. So if I take this state, the orbit is these four corners. So for example, this state here is then majorized by that state. But this is just one possible way of doing it, and there are much more sophisticated things being done that you will learn about. And in particular, it's also, this really does not address the question of how does that relate to the definition of the eigenvalue spectrum majorization. So if is it well defined to define it in that way in terms of an eigenvalue spectrum majorization? In what's going on there, I'm not sure, but I think that they do understand that in these talks that are coming up. And also there's a challenge here, a research challenge for thermodynamics when it comes to majorization. So one thing that already appears in the classical case, and I think when I changed these slides, I somehow dropped the citation to Ruch and Lee, who have done very nice work on majorization in thermodynamics in the 70s, where they're arguing that the second law as we have it now is not the right one, that actually the second law should be phrased in terms of majorization. So they call it the principle of increasing mixedness. And now there's a sort of revival of these sorts of things in the context of actually this single shot approach to thermodynamics. One of the problems that always comes up is that in thermodynamics the energy basis is special. For example, the free energy of state U minus Ts is not permutation invariant of the energy probabilities. You know, if you have like some probability of being in the excited state and some probability of being in the ground state, you can't just swap them around and say, oh, this is now as good a state or as bad a state as previously. So for example, the excited state has higher free energy than the ground state. So unfortunately in thermodynamics, you don't have this permutation invariance that normally entropy likes you to have. And there's actually a nice trick for getting around that, which is that you can introduce hidden micro-events such that lower energy states get more extra events. So these are this is a mathematical trick, the way I think about it. So it's kind of the equivalent of if you're in say the World Bank comes to your country and says, oh, you have really bad inequality, your Lorentz curve is really dipping like that. And then you say, oh, no, it's just that actually these rich people represent, 1 million people each. And then by introducing these fictive extra people, you can get a straight line. And you can do the same thing with the Gibbs state, with the thermal state. So you say, oh, it's actually this lower energy state, it has a higher probability, but that's because there are many, many states there. So then actually once you've done this operation, your Gibbs state becomes the uniform distribution, and your thermalizations modeled as stochastic matrices become doubly stochastic matrices. And then it's very clean to use majorization, because your thermalizing operations will be doubly stochastic and therefore respect thermalization, which is the tighter restriction, not entropy increase, which would be satisfied, but it's not tight enough. So we can get around that, and the thermal state becomes uniform. And then there's the same problem in when you have superpositions, that G and G plus E, they have the same density matrix eigenvalue spectrum, which is 1, 0. But one can extract different amounts of work from them. Okay, some people argue that you cannot extract work from coherence, but I think you can. So this is a kind of a research question, really, how to work out how to deal with that case. And there's a lot of work, interesting work being done. So, for example, there's a recent paper by Dahlsten et al. At Imperial. Okay, so is this the right time to get to the summary?
You've got a bit more time actually, it's fine.
Okay.
People are tired. Those of you who've done... Sorry?
Will you get a pay cut?
Okay, so to summarize, the P majorizes P prime. But the standard definition is this: that if you order the probabilities in descending order, then the sum for all k upper bounds the other one. Actually, now because I'm not going to digress too much, but I can just say one more thing about this formula that I forgot to say because I have a little time, which is that one way naive way of making sense of this is that if you want to say, oh, which distribution is more random than another, is that how quickly do they get to 1 as you sum them up. It's like a race, that the most ordered distribution gets to 1 faster as you add them up. So that's another way of remembering, but that doesn't capture the whole thing, because actually it has to be faster than the other one at all points. So imagine if you played sports that way. So it's like you can only win a tennis match if you were ahead throughout the whole game. I don't know if there's a game like, maybe rowing, there's some sort of, yeah, maybe there's some sport that does that. So in the quantum case it's the same, but for eigenvalues of density matrices. So this guy majorizes that one if the eigenvalue spectra majorizes the other one. And I forgot to put in for all k, okay? And then I argue that a lot of insight is gained by noting that these can be equivalently formulated as rho prime is a probabilistic combination of the result of applying reversible operations on the state in question. So in the classical case, these are permutation matrices, and in the quantum case, these are unitaries. These talks are in this conference. I think Carlo is giving this one. Which day?
On Thursday.
Thursday, and Howard, I don't dare to look in case he's asleep.
He's not here.
He's probably asleep outside. He got up very early from Greece. They're giving this talk, which has a very similar title to what I've just discussed, right? But this is going to be much more advanced. So I've been trying to sort of lay the groundwork for these two talks. I think that was it, yeah. So thank you very much.
Thanks very much, Oscar. John?
So this majorization concept lets you state a stronger version of the second law. And I was wondering if anyone had experimentally tried to find situations which were when transition was forbidden by the stronger second law, though not by the...
It's a great question. I'm not aware that anyone has. It would be great. I was hoping that that sort of thing would happen in protein folding, because they do like numerical simulation of protein folding. There they use what they call free energy landscapes to weight their hops. So I was thinking, oh, maybe they allow for these models. Maybe they include hops that shouldn't be allowed. Because free energy decreases is not sufficient for a thermodynamic transition to be allowed. It's only necessary. But then actually the way they do it is to use these stochastic matrices in such a way that the simulations actually respect the stronger condition. But that, I'm hoping there is something like that people have done incorrectly by assuming that free energy decrease is sufficient, but I'm not aware of it.
Maybe you will tell me I should just wait until Thursday, but I'll be gone by then. So I will ask the question concerning majorization in general theories. You told us it's not even clear how to define it, but in the case of classical and quantum, we have applications. In the case of classical, the two kings can fight off, decide who is more unfair. And in the case of quantum, about LOCCs, what would be applications of majorization for general theories? Forget about definition.
Yeah. I don't know, but I think that's the right question. Yeah. I mean, if you can, so I guess there's a movement to try and create thermodynamics of generalized probabilistic theories. So that would be one. I'm trying to resist saying that you have to wait until Thursday. Do you want to say a preview of anything that you can help to answer his question?
Well, I'm talking about my kind of approach to do that. So, this paper comes in some kind of framework towards defining some kind of reasonable way to have thermodynamics. And the first starting point was to define some kind of resource theory of entanglement and the related resource theory of purity in general probabilistic theories through LOCC protocols, and then to identify the axioms such that it's possible to have the same duality here for pure states, such that we can say that a state is more entangled than another, if and only if, when we reduce the marginal states, we have that the marginal state of the former is more mixed than the marginal state of the latter. More mixed means that it can be obtained through that kind of so-called group majorization, through some kind of random mixture of reversible transformation. And this is the operational part. Then the specific thought is how to relate this notion to as Oscar has said, the spectral majorization, defined as the majorization obtained through some kind of abstract version of the eigenvalues of states. So I'm trying to define the abstract version of the eigenvalues of states, since once we have that notion, we can export majorization, and I won't talk about that, but it's possible to prove that with the same axioms I will be talking about, it's possible to show that let's say group majorization implies spectral majorization.
But so is LOCC entanglement conversion is one example that you're looking at here. It's nice.
Okay, thanks. There's one more question up here. Alex.
Sorry if you already addressed this and I tuned out.
No.
But going way back, when you first were defining majorization, I think you may even sort of mentioned in passing, you can define a Gini coefficient for probability distributions. Do those have any connection with entropies? Any of the many entropies that we're talking about?
Do Gini coefficients have connections with entropies? I don't. Yeah, you feel like they should, but I don't actually know. But why not? Yeah, they probably, probably they do. But I don't know what the relation is.
They change if you're adding a bunch of zero probability events. I don't think entries do.
That could be an issue, but maybe you can get around that. Just how you define it.
Another question?
Is there anything to be said when two states can trump each other?
Anything to be said, like a general state?
Yeah, if it's possible to say about two states, and I can see they can trump each other.
So like a way to check whether they trump each other?
But I should have to check over all possible
right.
setups.
So I haven't checked the proof myself, but I think there is a theorem that if all the Renyi entropies bound each other in the direction that you expect, that then there is a trumping. I'm not sure if that's easier to check or not, but yeah.
Okay. We've got another last minute question.
Alright, so something you mentioned really briefly when you were talking about how, so for instance, just looking at the one moment entropy was not a good way necessarily to see if you can transform from one state to another, and that's kind of to do with, right, I mean, it's like an asymptotic kind of quantity on it, and so there's all this machinery of people who write papers about one-shot quantum information theory and other entropic quantities to look at that when you have a finite number of copies. So is that, do those things, is there any relationship between quantifying majorization via single shot quantum information quantity?
I think that's a really good question. So the relation I know is from thermodynamics, that these measures of majorization reduce to single shot quantities for certain cases. So the relative mixedness reduces to the conditional, the relative order zero Renyi entropy. If you comparing if the final state is uniform. So, yeah, I might have to write it out for you. Basically, they reduce to and that reduces to log d minus s0 in another limit. So there is some relation like that, and I don't know if that has been done in the information theory context, but in this thermodynamics, it's the case.
Okay, thanks very much. Thanks to you all for listening. Thanks to you guys all for speaking.
Thank you for inviting me.
And let's thank all the speakers again. Have a nice evening, everybody, and see you in the morning at 10 o'clock.